We're going to talk about blood flow distribution. So I've changed the title of this slide. So blood flow distribution, basically what we're talking about is where the blood goes. You've got a certain amount of blood. You've got about 5 liters of blood in the body, and the body has to do several things with that blood. Depending on the demands on the body, blood flow will be distributed to different parts to meet the supply, to meet the needs. And the distribution of blood flow is mostly controlled by the radius of the arterioles, okay, because the arterioles are delivering blood to various parts of the body. And arterioles have smooth muscle in the walls. So the walls of an arteriole have smooth muscle. And if the muscle contracts, the arteriole gets smaller. Okay? The smooth muscle in the wall contracts, the arterial radius gets smaller, which reduces blood flow that's going wherever that arteriole is going. So blood flow is primarily controlled by small changes in arterial radius. And the effector, which is the smooth muscle, is controlled by the sympathetic nervous system, and we'll come back to that. So when a arteriole is told to contract, we call that vasoconstriction, okay? And the smooth muscle contracts, which causes the diameter to get smaller. That's what this is here. And therefore, the vessel, that particular vessel, is going to have less blood flow going to it. So whatever part of the body is receiving blood from that vessel is going to get a reduction in blood flow. And this is contraction, and so this is an active process because it uses ATP. On the other hand, we have vasodilation. And with vasodilation, what happens is the smooth muscle relaxes. And when the smooth muscle relaxes, the diameter gets bigger. And therefore, more blood flow is going to go through that arteriole. And therefore, whatever part of the body is receiving flow from that arteriole, that part of the body is going to get more blood flow. This process is passive, okay, because the muscle is simply relaxing. Okay, so contraction is active, relaxation is passive. And this is how blood flow is controlled within the body. Certain parts of the body are going to have vasoconstriction and a reduction in flow, and other parts of the body will have vasodilation with an increase in flow depending on the needs of the body at that time. So here we have two circumstances. We have rest and we have heavy exercise. Remember that everybody has about 5 liters of blood in your body, and on average. And at rest, a normal cardiac output at rest would be about 5 liters per minute. So what that tells us is that at rest, your blood flow goes all the way through your body about once a minute. And now let's look to see where the blood flow is distributed. So if we take 100% of your flow, which is 5 liters, at rest, 20 to 25% goes to your viscera. Okay, your liver, your stomach, your intestines. 4 to 5% goes to the heart, 20% to the kidney, 3 to 5% to the bone, 15% to the brain, 4 to 5% to the skin, and 15 to 20% to the muscle. And so if the muscle is receiving 15 to 20% of 5 liters per minute, at rest, the muscle receives about 0.75 liters per minute. So using this as a baseline, let's see what happens during exercise. And again, we're going to do an extreme example. We're going to look at heavy exercise. And in this example, blood flow is 5 times faster. So cardiac output, instead of 5 liters per minute, is 25 liters per minute, which means your blood circulates through your body about 5 times a minute during heavy exercise. Now let's look to see how blood flow distribution has changed. We get much less blood to the viscera. Okay, so the stomach, the liver, the intestines, the kidneys are getting significant reduction compared to what they had at rest. Okay, the heart is getting about the same percentage, but because the blood is flowing much faster, and therefore the body sees 25 liters per minute instead of 5 liters per minute, there's actually an increase in blood flow to the heart during exercise. So 4 to 5% of 25 liters is a larger amount than 4 to 5% of 5 liters. So the heart's getting more blood flow. The bone gets a reduction. The brain gets a reduction. The skin, we're going to come back to the skin, but you can see there's a huge variance in how much blood flow goes to the skin. And that's based on heat and how much the body is heating up. But blood flow to the skin may change very little, or it may change a lot. Okay, so the more the body heats up, the more blood has to go to the skin. So if we're looking at 5% flow, you're looking at somebody in like a 50-degree environment, and the hotter the environment and the more humid the environment, the more blood flow. So on the extreme end, the skin may have to receive up to 20% of flow to help the body cool, but we'll come back to that. And then you can see that the largest change during exercise are the muscles. Okay, so the muscles, where they got 15 to 20% of 5 liters at rest, now they're getting 70 to 85% of 25 liters, okay, which comes out to 20 liters per minute of blood going through your muscles during heavy exercise. And I hope you can see that that's significant increase in blood flow to the muscle. Okay, that's because the priority changes. So during exercise, the low priority areas are going to get less, and the areas that are most important during exercise are going to get more. Okay, particularly the muscle. And I just want to note here, this is part of the reason why you don't want to have a big meal right before you exercise, because if you have a big meal, you're going to get some blood flow to the viscera, okay, because of digestion, and you're going to have to share some of that blood flow. So some of that blood flow that could be going to your heart, to your skin, to your muscle, is going to go to the intestines to try to digest food. At the same time, because you're fighting to send blood to those working muscles, the digestive system's not going to get as much blood as it normally would during digestion, so it becomes harder to digest your food. So blood flow distribution is primarily determined by the diameter of the arterioles feeding that area of the body. So the next is, what is determining whether or not a arteriole contracts or relaxes? So as I said before, the arterial smooth muscle is controlled by the sympathetic nervous system. So when the sympathetic nervous system is firing, which as you know is always firing to some degree, the SNS causes contraction, constriction, and some amount of vasoconstriction. Okay, so smooth muscle contracts, So we get vasoconstriction. Okay, and even at rest, we have some SNS outputs. Very small, but we have some SNS output. So your smooth muscles in your arterioles are always contracted to a certain degree, although it's very low. Okay, there's a certain amount. The muscles in the walls of the arterioles are never completely relaxed. There's always a little bit of what we call SNS vasomotor tone. This helps maintain blood pressure. And we'll talk about blood pressure later in this chapter, and you'll learn that if all the blood vessels in your body relaxed and everything opened up, blood pressure would drop significantly and blood flow would stop. Okay, because you would lose all of your pressure gradients and all of the driving forces that move blood through your body. So you need to have some vasomotor tone at rest. When you exercise, we get an increase in SNS output. Okay, so you're going to get more vasoconstriction to your arterioles, which is going to cause a reduction in blood flow. And that sounds good. That sounds fine. This is a decrease in diameter. Except that there are some areas of the body during exercise that need more flow. So if SNS causes vasoconstriction and a reduction of flow, that's okay for your viscera, but how does the body work to get an increase in blood flow to the areas that need it? And that's where intrinsic. All right, so intrinsic control means that the arterioles themselves, just like how the heart has an intrinsic heart rate and it can establish its own action potentials, the arterioles have their own intrinsic ability to control their own regulation. And we call that autoregulation. I don't think your book uses that term, but I like the term autoregulation. And what it is it's the ability of the local tissues to cause the dilation of their own arterioles and therefore increase blood flow when there is a need for that tissue to have more blood flow. So there's three different explanations for intrinsic blood flow, or intrinsic control. We're not going to talk about these two. We're going to focus on this one, which is the primary cause. And basically what this is, it's a negative feedback response. So based on the conditions, the local conditions of the tissue that is being served by an arteriole, the arteriole is going to be told to contract or relax. So the types of stimuli that cause this to happen are the things that are happening during exercise. So during exercise, you're going to get a drop in pH. You're going to get a rise in hydrogen ions and lactic acid. You're going to get, and this is an error actually, you're going to get a drop in oxygen. Okay, because as your body starts to use oxygen, the oxygen levels in your body start to drop. So during exercise, you're going to get a reduction in oxygen, you're going to get an increase in CO2, and you're going to get an increase in temperature. And all of these different things trigger a negative feedback response. So pH, lactic acid, oxygen, CO2, those things are being monitored by chemoreceptors. And temperature is being monitored by thermoreceptors. And so when the chemoreceptors or the thermoreceptors in the area sense these types of changes, it triggers a negative feedback response to try to counter these changes. So what's going to happen is the effector, in this case, is the smooth muscle, the arterial smooth muscle. Okay. the effector is going to receive a response, an intrinsic response, and that intrinsic response is going to tell that smooth muscle to vasodilate, to relax, and vasodilate. Okay, so remember, we're exercising, so we've got that SNS response. And SNS is telling all the arterioles in your body to vasoconstrict. But areas in your body that are experiencing an environment like this are going to override that vasoconstriction on their own through autoregulation. The receptors, the chemoreceptors, the thermoreceptors are going to detect these types of changes occurring in that area, indicating that area needs more blood flow. And the response is going to be that the smooth muscle, which is the effector, is going to be told to relax and vasodilate, which is going to cause more flow, more blood flow through that arteriole, which is going to result in negative feedback. Okay, so the drop in pH is going to come up. pH is going to go up as you're able to flush out some of the hydrogen ions. So you're going to have less hydrogen ions, less lactic acid. You're going to be able to bring in more oxygen, get rid of more CO2, and you can also get rid of more temperature. Okay? There's your negative feedback response. Okay? And this was an intrinsic event. This had nothing to do with the central nervous system. It all occurred right there in the local tissue, the tissue that was being fed blood by this arteriole. We call that intrinsic regulation. So let's say a little bit about the second way blood flow is controlled intrinsically is through what we call local capillary recruitment. So every muscle, every tissue in the body has capillaries feeding it. So the arterioles feed into capillaries and tissues. So this particular tissue has 7 capillaries. Normally at rest, only about 5 to 10% of the capillaries feeding muscle tissue are open. Okay, so normally at rest, most of those capillaries are closed because capillaries have muscular walls. They have precapillary sphincters, which are muscles that can contract and close. And this is another way that blood flow is controlled. So if a tissue is not working, if a muscle tissue is not working, there's no reason to use all of the capillaries. During exercise, what happens is also through autoregulation is that the capillaries start to open. So during exercise, an increase in the percentage of the capillaries are open. And this is another way that we can get more blood flow to that active tissue. So we've got the autoregulation of the tissue itself, which causes vasodilation of the arterioles that are feeding the capillaries. And we also get a recruitment of more of the existing capillaries, which helps to take in that additional blood flow that's coming from the arterioles that have been vasodilated and therefore have more flow. So during exercise, your body generates heat. Okay, we've already talked about that. And if you exercise for a long time, heat production eventually exceeds heat loss. And so heat is going to accumulate. your body temperature is going to go up. Also, if you exercise in a hot and in humid environment, this is going to happen even sooner. Okay, so you don't have to exercise as long in a hot or humid environment for your heat to accumulate, because in a hot and humid environment, it's harder to dissipate heat. So the same way that we talk about blood flow and the pressure gradient, blood going from high pressure to low pressure, heat also moves with a heat gradient from high heat to low heat. And so it's much easier to get heat off of your body when your body's hot and the environment's cold, because it's very easy to move heat from high heat to low heat. But when the environment itself is hot, this results in a smaller heat gradient and a lower amount of heat loss. There's a less of a driving force for losing heat, so you're going to get less heat loss. So it's harder for the body to maintain temperature in the heat. And the humidity, the key to humidity is that now we're looking at your ability to sweat. Okay, you're going to sweat, but I should say your ability to evaporate your sweat. Okay, so the way you cool yourself is you sweat and then you evaporate the sweat, and when the sweat evaporates, it cools yourself. If the environment is humid, then the environment is wet. And again, we have this pressure, not a pressure gradient, we have this water gradient. Okay, you've got wet skin and you've got a wet environment. It's harder to evaporate wet sweat when the air is also wet, because you go from high wet to low wet. And if the more humidity there is in the environment, the less of a gradient you're going to have for evaporating your sweat, so it's harder. So what happens during exercise in these situations is you have to get more blood flow to the skin. So the arterioles feeding the skin are going to start to dilate and open up. And remember that you only have about 5 liters of blood that you can distribute. And so if you're distributing more blood flow to the skin, that's got to be taking blood flow from somewhere else. Okay? And in particular, during exercise, that blood flow is going to be diverted from your muscle, from your heart, the areas that really need it for working. So you're going to get a reduction in blood flow to working muscle in order to send more blood flow to the skin to help your body cool. And this means you're going to have a reduction of supplies going to the muscle. Okay, you're going to be delivering less oxygen, glucose, fat, and you're going to be removing less lactic acid, hydrogen ions, and CO2. And this is going to have an effect on performance. So you can see why when the environment is hot and or humid, your performance is going to suffer.